Hey everyone, so this is going to be the last video on electrostatics. It's just a little bit extra with electric potential. So once again, you should have seen the video where we went over the equation and all that. I just wanted to mention a few more things though before we continue. So first, uh, the important thing is to realize that this is not energy. You might accidentally think that because of the word potential that this is related to potential energy. No, it's a completely different thing. Um, Usually we talk about electric potential difference. It actually goes by so many different names. Uh, it is related to energy. It's actually defined as the amount of energy per unit of charge required to move objects between two different points. Um, but it's not really an energy. It's actually more of a description uh, or a statement about how likely objects, charged objects, are willing to move between 2 points. In fact, one of the things that electric potential is usually related to is gravity and height. So just like how with gravity and height, how when you have an object at a height or at a different gravity, it does end up gaining a potential energy, but the height doesn't have energy inherent to it. So that's kind of what's going on here. The electric potential by itself does not have energy because it's just a point in space. It's when we move a charge to that potential where it starts having energy. So that's the important note, is that the electric potential is a description of a certain point in space. There's no energy to have because there's no object at that point anyway. And just like how the difference in height and difference in gravity is what causes objects to move from one point to another, same thing here. If there's a potential difference, objects are going to want to move. And the bigger that difference, the more likely they are to move. Now, again, super big warning, electric potential is not the same as potential energy. Uh, like I said, this is extremely important because they're in the same equation together. The equation has electric potential and electric potential energy, V and W. So you want to make sure that you're plugging the values in into the right spot. Now, for the very first time of all, you should know that the potential represented by the symbol V actually is the only symbol that we have that has the same symbol unit. Volts and voltage are both represented by V. Again, only one that's like that. Typically, you have things measured in units that have no relation to the symbol. This one's the only one that does. Now, the thing that I want to actually talk about, besides that little warning, is this thing called equipotential lines. It's not super common. It's actually fairly rare, but I just wanted to make sure I said it at least once. Equipotential lines, as its name implies, if you break it down, equi means the same, potential means potential. These are lines that are representing the same potential throughout. Now, I mentioned before that how the field lines that you've drawn for electric fields and for gravitational fields are like contour maps with all that stuff. This is actually exactly contour lines, because just like with contour lines where a line represents the same height, this represents same potential, which, as I mentioned before, is pretty much the mass equivalent to height. So this is kind of what equipotential lines look like. So you still have the straight lines with the arrows for the electric fields going from positive to negative. Here's around a point charge. All the lines are going outwards. But then you have these dotted lines that kind of go perpendicular to the field lines. Here they go up and down vertically, and then around the point charge they kind of act like concentric circles. Again, this means that everywhere along here has the same potential. That if you put an object here and an object here, they're going to have the same potential, and as long as they're the same object, same potential energy. If you put them here and here, again, they're going to be at the same potential, just like how they would be at the same elevation. They have actually a very specific thing, though. A unique characteristic is that any object that's moved along an equipotential line requires no work. And that's because we said before that work is done, energy is required for an object to move from one potential to another. If you're not changing your potential, though, you don't need any work. This is very similar to if you actually lift a book off the table, that requires work because you're changing the height of that object. But if you maintain that the height of the book and you move it to the other side of your room, that requires no work because you're maintaining the same potential energy throughout. You're not changing the height of that book. Just like that scenario, here moving along an equipotential line, you do not change the voltage, therefore it requires no work. It's free movement essentially, and that's it. Like I said, it I don't really see equipotential lines coming up too much on the regents. If if you're unlucky, it'll probably be only one question, and most likely it would be left as a throwaway question, either a hey, which one of these diagrams represents equipotential lines, or just the idea of what is equipotential lines, and you choosing the choice that says the voltage doesn't change. So, like I said, I just throw it in there just in case, but the likelihood of you seeing it is very rare. But I just want to say it just in case. So, that's it. If you have any questions, feel free to let me know. Message me on mine. Otherwise, good luck. Have a great day.